All right. Sorry?
I was like, maybe you could write something on the side like somebody shouting at you, turn on.
Yeah, I know. Sorry, I forgot to start. All right, so real quick, if you're just tuning in, that's where we started. Pause, look at it. There you go. All right. That's all I got time for. All right, so first of all, I noticed something useful here. All of the M's cancel out. Ooh, that seems nice. Okay. So now I've got 1/2 v squared plus beta times 1/2 v squared. So I'm looking at this. GH equals 1 plus beta times 1/2 v squared, yes? Yep. So again, right now I'm walking down the path of finding that velocity at the bottom of the rank. Everybody good? Yes. Okay. So multiply both sides by 2 and divide by 1 plus beta, and you get 2gh over 1 plus beta equals v squared. And we could certainly take the square root of both sides of that and find the velocity. Yes? Yeah. Okay. I just heard a what? Was that 8? Maggie? Are you, was that a, what's up? Talk to me. Okay. All right, everybody happy? All right, so, but the problem is we don't know what h is, right? Like that wasn't sort of one of our given things. So we need to replace h with delta x sine theta, okay? So I'm going to go one more step here. So 2g delta x sine theta over 1 plus beta equals v squared. Haha. All right, so we now have our velocity, yes? Yeah. Are there any problems? What's wrong, Carl? It is a lot. All right, like I said, alphabet soup. But you guys, like if we had the numbers, we certainly could have done this and plugged in the numbers, right? Everybody cool? Yeah. All right, next step. Let's find the acceleration. All right, and it turns out, this is the super secret ninja trick, that if you had used actual numbers, you wouldn't have had to do the algebra I'm about to do. But, so this is our VF, right? Yep. Aha! Oh! Right? VF squared is 2a delta x, right? Aha! So, oh no, that's not what I wanted to do. Oh, that's also not what I wanted to do. There we go. No. So VF squared is 2a delta x, yes? Yep. So I'm going to rewrite my new equation. Here's what I've got now. 2g delta x sine theta over 1 plus beta equals 2a delta x. Yeah, what cancels, you guys? The delta x cancels. And the 2 cancels. So now I've got A equals G sine theta over 1 plus beta. Follow? Yeah. All right. So if we had had numbers, what you would have done is you would have just said, oh, well, I know VF, I know my delta x. So you do 2a delta x equals VF squared minus VI squared and find your acceleration. Okay? What's up?
Do you do like 1/12 and 2/5 or 1/3?
Yep.
Like that?
Yep. It's the fractions from these fractions in front of those guys.
Oh, okay.
Follow?
Yeah.
All right. Everybody good? All right. So now how do we find alpha? Just divide by, oh wait. A equals alpha r, right? Not the other way around. A equals alpha r. So that means alpha is A over r. So it's the same as this, but just divided by r, right? Yes. Cool? Okay. So, cool. So we found a bunch of stuff here. This is cool. We found VF, we found A, we found alpha. So now the last thing that remains to find is our force of static friction. Yes? Yeah. All right. So to do this, well, you guys tell me. What we're looking at forces. What would be a great first place to start? Net force equals net force, right? Make a free body diagram and do net force equals net force. Good?
Yeah.
Question, Patrick, or is that what you're just going to?
I just saw the way, I don't know what it's like.
Yeah, you're mumbling.
Well, like it would have a certain acceleration going down forced in active bottom, so it's kind of like against the acceleration. I don't know, but it's rotating, so no.
All right, so let's do this. No, I agree with everything you just said. We're gonna get there in 1 second. All right, so suppose it was just sliding. All right, so here's our thing. All right, if it was just sliding, what would the only force on it be? Force of gravity, right? So, but ultimately, which component of the force of gravity do I care about? Just the parallel component, right? So now it's important where the force acts. So at what point should I draw my force of gravity? Center of mass, right? So here's my center of mass. Here's my FG parallel. So that's just mg sine theta, right? Follow?
Yeah.
So if it was just sliding, like if this was a box instead of a wheel on a frictionless thing, then the acceleration would be this divided by mass, right? So it'd be g sine theta, right? Follow? What is our acceleration? Our acceleration isn't g sine theta, it's g sine theta over 1 plus b, so it's slightly smaller, right? Notice if beta was 0, in other words, if there was no rotational kinetic energy, then we'd get g sine theta for our acceleration. Hooray, physics. Good?
Yep.
Everybody good? I know there's a lot going on here. Are we good? Yeah, Anthony.
So, like, I'm guessing we'll probably never have a point particle rolling, because then it would just be sliding.
Correct, yeah. Because in order to roll, you have to have a radius,
Yeah, okay.
and a point particle by definition doesn't. All right, everybody good? All right, so,
You know what, dude? I'm just trying to follow.
okay, so, now what's happening here, you guys, is it's not sliding, it's actually rolling, right? And the reason it's rolling is because you have to have friction. So at what point should I draw my force of friction? At the bottom, at the point of contact, right? Good? All right? And remember, we know our acceleration is g sine theta over 1 plus beta. And I've got a missing force. So, again, we already said it, but how do we find it? Net force equals net force, right? All right, so let's do this. And it seems like it's going to be ugly. It ends up not being quite as bad as you would think. So it's net force equals net force. So MA equals FG parallel plus FFS, right?
Yeah.
Wait. One of them has.
Sure, yeah, you can put minus if you want. I was just thinking it had negative, but yeah. Sure. I'm cool with that. I think you're right. I like putting the negative there better. I was just going to make down the hill positive and up the hill negative, and we just solve it and get a negative force of friction. But whatever, it doesn't matter. All right, are we good?
Yeah.
I just want to make sure they're good before we move on. We're doing a lot here, so I want to make sure everybody's up to board or up to speed. Is it related or a weird tangent? What do you got?
He's trying to figure out why the overall like, full object moves down the ramp slower than it would.
Gotcha. Okay, so let me give you two. So the question is, why does it move slower when it's rolling than it does sliding? Is that what you're asking?
Yeah, I get the whole thing with the energy, but I'm just confused.
Okay, so yeah, so let me give you two answers. So answer number one is in terms of energy. If it's just sliding, then all of your GPE becomes just regular KE. So you're purely converting energy of height to energy of motion. Okay? Whereas when it's rolling, some of the energy of height becomes motion and some of it becomes rotation. Okay, so that's the energy explanation. Good? All right. The second answer is, I think, what Daniel was explaining. Do you want to say what you were explaining, or?
It's kind of a weird explanation, but sure. So like, if you imagine like you have like, say a hoop, I think that makes it a bit easier. So you have like just a series of particles going around in a circle forming a hoop. So if you imagine a particle at the bottom in contact with the ramp and one at the top, right? That one at the bottom is in direct contact. It's experiencing the force of friction, pushing it back, slowing it down. The one at the top is not experiencing that in the same way. So you get that difference in, if you were to imagine, like, it gets a little weird because they're bonded together.
Right.
But for the sake of keeping it simple, there would be a difference in those velocities that create that rotation, and then eventually that one at the top would come down and also make that contact slowing down. And on average, every single
Particle gets slowed down at some point. That's
overall
cool.
velocity is less as well.
That's cool. I like that.
Yeah.
All right, Patrick. The answer I was going to give is just thinking about it in terms of net force. Look, there are two forces in the direction of motion: gravity pulling it down, and friction resisting it. It's got to go slower because friction's slowing it down. All right. So, is everybody okay up to here? All right. So let's finish this. All right. So, I'm going to plug in my numbers, you guys. So MA. So M times A is G sine theta over 1 plus beta, right? Good, so that's my MA side. Equals FG parallel. Well, that's mg sine theta again. Follow? Minus the force of static friction. All right. So do you guys see that mg sine theta is bigger than mg sine theta over 1 plus b? And the difference between those represents the force of static friction? Everybody okay with that? I'm going to skip a couple algebra steps and give you the simplified answer to this, if that's okay. Okay? So if you simplify this, here's what you get. You get that the force of static friction is beta over 1 plus beta times mg sine theta. So, but the point is, an amount of friction that we can calculate. Follow? Yay, I know, right? All right, are we good? I know this has been a long example, but I want you to see all the pieces here. So, are we good?
Yeah.
All right, so, remember 7 hours ago I told you that there were two ways you could think about the rotation? All right, so at the start of this, Cam, are you good? You're making a scrunchy. What the bleep did he just do face?
I'm just confused on how you got
From here to here?
Yeah.
So this is 1 over 1 plus beta times a thing. And this is 1 times a thing. So when you do 1 minus 1 over 1 plus beta, it gives you beta over 1 plus beta. Does that make sense or no? If you factor out the 1 plus beta, I think you'll see what happens. And you got to do common denominators, right? This is 1 over beta plus over 1, or 1 plus beta over 1 plus beta. Do you guys want me to do it real quick? No, please. Okay. All right. Okay. So 7 hours ago, I commented that you can treat your pivot points as one of two places, right? And when I started this problem, I said, let's treat this with the center being our pivot point, right? Okay? So check it out, you guys. What forces are acting on this thing?
Gravity.
Gravity parallel. And friction. All right? Now, my net torque then is the torque from gravity plus the torque from friction, right? All right? So what's our torque from gravity going to be with this pivot point? 0. Torque from friction. Well, where is my lever arm? Isn't it just the radius? And notice it's perpendicular to the force, isn't it? So this goes away. My torque from gravity is my force of static friction times the radius, right?
Wait, why'd you cancel the friction?
Oh, shoot, sorry, I canceled the wrong thing. Thank you. Sorry. Torque of gravity plus torque of friction. Sorry, this one goes away. Thank you, sorry. All right, so torque of friction is force of friction times radius. Bear with me, this is going somewhere, I promise. You guys are being really good sports. I know this is a lot. So you get beta over 1 plus beta times mg sine theta times r. Yes? Yeah. So that's my net torque. What's wrong, Carla?
What is FFR? What is that?
Torque is force times distance.
Oh.
So I found the torque of friction by doing force of friction.
Why did you cancel or torque of gravity?
Somebody help out. Why is the torque of gravity 0? Because your lever arm is 0. So, yeah, so remember, torque is always force times distance, right? So if this is my pivot point and I push here, then my torque is lever arm times force, right? Good? What happens if I push here? Nothing. That's what's happening with gravity. My pivot point is here, and gravity is pushing at that point. Is that going to cause it to rotate around that point? So the torque from that is 0. It's force of gravity times 0. Follow? Are you lying? Is everybody good with that? Everybody good? All right. All right. Is everybody good with the net torque? Carly, you're still making the scrunchy face. Patrick?
What was the last thing you did?
Sorry?
Can you go up one? A little higher? To the last thing.
Oh, like back a slide?
Look, you don't know what I'm doing. Maybe you don't know. You don't know. I'm from Manchester. You don't know.
I don't know. Yeah.
Why did we not find that torque?
Oh, thank you. I'm sorry. So while you're figuring this out. All right, so we'd already found all the things we were looking for, right? Good. But we haven't yet looked at, like, the reason this thing rotates is because of torque.
But why didn't we just do what we had already found with,
I want to show you, so where I'm headed now is I want to show you that the torque equations give the same result. And we're like one step away. Okay? All right. McKeever, let me talk to you at lunch, if that's okay. Is that all right?
Yeah.
Okay. All right, so is everybody okay with how I found my net torque?
Yes.
So, net torque equals net torque. What am I going to set this equal to? I alpha. Let's see if our alpha agrees.
oh, we're just doing this for shiggles?
Yes, exactly, for shiggles. Thank you for censoring, because I wouldn't have. All right, so. I do too. All right, so net torque is I alpha. So here's my net torque. So beta over 1 plus beta mg sine theta equals I. So I is just beta times mr squared, right? So let's see. And then the question is, does our alpha match? So let's solve this mess for alpha. So what do you notice? Betas cancel. Masses cancel.
One of the R's cancels.
Oh shoot, I forgot my R. Thank you. Here, when I wrote my net torque, I forgot an R.
One of the R's.
So now one of the R's cancel. So you get R alpha. So let me highlight what we're left with. So you've got R alpha equals G sine theta over 1 plus beta. What's R alpha? Acceleration. Oh, it's G sine theta over 1 plus beta. Same thing we got before.
R alpha, how did you know that was?
It's a jumper equation. R alpha is always A.
Alright, cool.
Good? But, okay, but why? So you ought to be able to do all this with numbers, right? Like if I give you, a hoop rolls down a ramp that is 2 meters tall. What's the velocity at the bottom? You ought to be able to find that. What's the force of friction? You ought to be able to find that, right? So that's what we just went through. We went through like 8 problems here, which is why this took 7 hours. All right? Questions? All right. So here's the deal. So that's one of the 2 options. And I know you guys are all about grown. So that is, what we just did is solving it as though this is the pivot point, right? So now the question is, what if you treat this as the pivot point? Hold on. So this, in my notes, this was like 2 written pages. The other one's like half a page. Okay? The other one's really quick. Okay? I think I'm going to melt your brain, though, if I try to do that now, yes?
Go for it. Don't melt us.
How many know I'm trying to muscle through? Let's do it. All right, let's do it. Yeah.
Onwards to victory.
Okay, we're almost done. Well, we got to focus.
To glory.
All right, so here's all we're going to do. So if we treat it as pivoting about this point, check it out. Here's my pivot point, right?
Yeah.
So there are 2 forces. There's the force of friction and the force of gravity. Which one don't I need to worry about now? You don't need to worry about friction now, right? Because it's at my pivot point. Okay? So my torque is just Fg parallel times radius, right? And that ought to equal I alpha.
Right.
Okay? So all we got to do is find I. Is it still beta mr squared? No. Good. Why? Parallel axis theorem. Right? Because it's beta mr squared is around this point. Right?
Yeah.
Around this point, you got to use parallel axis theorem. So here we go. So our I is going to be beta mr squared plus mh squared. What's h? R, right? Oh, well, that's just 1 plus beta times mr squared. Which, good. So that's our new I. That's the rotational inertia of the ball or whatever this thing is about this pivot point. Good? All right, so now I'm just going to do net torque equals net torque. Net torque equals net torque. So let's see. So force of gravity parallel times radius equals I alpha. Good? Fg parallel is mg sine theta times r equals 1 plus beta mr squared alpha. We're trying to solve for alpha, right? So let's see, our m's cancel. One of the r's cancel. Divide both sides by 1 plus beta, and you get the same thing. All right? Follow?
Yeah.
So, if you can solve it this way, it's a cool secret ninja shortcut. Weirdly, for most problems, even though that other way seemed way longer, usually for most problems, the other way is more efficient. Not always. All right? So that's 2 different strategies you can use. Questions, you guys? All right. Give yourself a high five, because that was badass. We just did a ton of this. That was cool.